Hello students, welcome back to computer organization classes. So the next topic is about distributed arbitration. So we were talking about the bus arbitration process. The previous one was the centralized arbitration. Please watch my previous videos, earlier videos. So here in case of distributed arbitration, all the devices participate in the selection of the next bus master. So in case of centralized bus arbitration, what happens is the processor is considered as the default bus master, and processor is responsible for allotting the mastership to other members. Whereas in case of distributed arbitration, the condition is different. Here the case is different, where all the members are equally responsible for handing over or transferring of control to the next member. So each device on the bus is assigned a 4-bit identification number or ID. When one or more devices request a bus, this assert start arbitration signal. Okay, this signal will be asserted and place their 4-bit ID number on the 4 open collector lines. As you can see, the horizontal lines ARB0, ARB1, ARB2 and ARB3, they are called as the open collector lines. And start arbitration, the fifth one, you can see there are 5 horizontal lines, right? Arbitration 0 to arbitration 3, 4 bit identification for each device, and start arbitration signal for asserting. Okay, so a winner is selected as a result of interaction among signals transmitted over these lines. The meaning is the open collector line, the one once the ID on open collector line and device ID matches, that device is allotted the mastership. That's it. Very simple thing. Each device will be having a 4-bit ID, and it is connected to, all the devices are connected to common open collector lines. So the value on open collector line, right? The ID that matches the open collector line, the corresponding device will be in the contention or mastership. So bus mastership will be transferred to the particular device. Very simple thing. Okay, here the example also given. Please go through this explanation. If you have any doubt, you ask. Okay. Then synchronous and asynchronous bus, two types of bus we are supposed to study, synchronous and asynchronous. So synchronous stands for frequent updation, asynchronous is the one which will not be having a frequent updation like, that is clock. Okay, in case of synchronous bus, an additional signal used, that is clock, whereas in asynchronous, clock is not available. Only the read write lines will control the operation in asynchronous bus. So let us begin with the synchronous bus. All the devices deriving timing information from a common clock signal, as I told you earlier. So synchronous bus will be having a concept called as clock. Equally spaced pulses on this line define equal time intervals, right? During a bus cycle, one data transfer can takes place. As you can see the diagram of input transfer of a synchronous bus, the timing is divided. You can see the clock, one complete cycle, there is a positive cycle and negative cycle. So half cycle is marked as a one interval. Starting point is t0, the half cycle centralized point is t1, and the end is t2, right? Where the entire cycle is utilized for transferring of address and command, and as per this, half cycle is enough. The second half, which is negative half cycle, whatever it is, duration between t1 and t2 is sufficient for transferring of data, right? Once the address and commands are exchanged, address in the sense source, where is the source, where is the destination, and other necessary commands, such informations will be exchanged in the particular interval, entire cycle is utilized. Whereas once the address command interchanging started, data exchanging will be initiated. So the data exchanging will be deactivated, process will be inactive between t0 to t1, but it completes between t1 to t2. So transfer of input control, of an input transfer of, in case of synchronous bus. So master slave configuration is given, right? master slave configuration, one sender, one receiver, master slave. Okay. Bus clock, the common clock is used for both the devices, say sender and receiver. Okay. Address and commands as seen by master. So address and command, it starts at interval t.am. Okay. A small delay you can observe, right? A small delay which is ignorable. Address and command exchanging will be done between the entire cycle as we have discussed previously in the same way. Then after that data exchanging will be initiated by the sender. Data sending process will be initiated by the sender, but again a small delay you can see. Okay. This is what at slave side. Again the delay factor is included, as you can see. This timing diagram is sufficient. You have to explain the timing diagram. What is that at T0, T1 and T2? What happens at T0, T1 and T2? That you have to explain. Please go through these explanations and all. If you have any doubt, please ask. This is the another example for multiple cycle transfer for read operation. As you can see, the multiple clock cycles, 4 cycles are marked, 1, 2, 3 and 4, right? So transferring of address and command, it takes multiple clock cycle. Earlier it was considered that one clock cycle is sufficient for transfer of the control and command and addresses, but now this data transmission, I mean transfer of control and command, which take more than one clock cycle, and that is what multiple cycle is. So it almost uses 3 clock cycle or 3.5 you can say, right? A small delay, fraction of delay you can see at first clock cycle for address and command, and almost it is completed at 4th clock cycle, right? And data transmission is done. See, initially address and commands will be transferred, then followed by data transmission will be completed. So data transmission is done after certain interval, say 1 or 2 clock cycle. After 2 clock cycle, as per this scenario, data transmission is initiated. So once the data transmission is initiated, at the same interval, slave ready signal also will be initiated to indicate the slave be ready to receive the data. Since you know about the master slave configuration, right? Master slave means one is serves as master, other one serves as slave. So master is the one who is responsible for sending something or providing some service, and slave is the one who is getting service from somebody else, right? So once the data session initiates, at the same time slave ready signal also will be asserted, just to indicate the other person who is acting as a slave to be ready. That's it. The same thing is explained here, what will happen at clock cycle 1, 2 and so on. Please go through it. That's all about the synchronous bus. Next we have asynchronous bus. So here in asynchronous bus, please remember there is no clock signal in case of asynchronous bus. Only two control signal, two signals act as control signal. One is master ready signal, other one is slave ready. Okay, master ready is used to indicate that master is ready for transaction or data session, and slave ready to indicate the slave is ready for a data session or transaction, right? Here you can see the diagram, timing diagram. As I told you, there is no clock cycle. Don't include the clock cycle. So you have to include only the master signal, master ready signal and slave ready signal. Based on it, the timing will be generated. Okay, intervals will be generated, and in case of clock cycle, synchronous interval, all the intervals will be of equal width. But in case of asynchronous bus, so since there is no clock signal, you cannot have the equal width of time or interval. Okay, you may be equal width or may not be. Both the scenarios are possible. So address and command will be transmitted. There is no clock cycle, so randomly address and command will be transmitted. Soon after the transmission of address, master's ready signal will be asserted. So this is considered as one interval now. So once the process initiates or process begins, that interval is marked as T0. Now once the master ready signal is asserted by the master or the device who is serving as a master, so that interval is marked as T1 now. right? This master ready signal will be deactivated after certain interval. We call it as T3. You just go through the diagram, you will come to know. So once the master ready signal is asserted by the master or device responsible for sending the data, the other member, the device who is responsible for receiving the data, also should assert a signal to indicate the master that he or that device is ready to receive the data. So immediately after that, after certain interval, the next interval T2, you can find slave ready will be asserted, right? Slave ready will be asserted. Once the slave ready is asserted, data session will be initiated at the same interval. So at what interval data session is initiated? Data session is initiated at T2, because the slave is ready. Slave ready signal is asserted at T2. At the same time, at the same moment, data session is initiated by master. This is how we can derive the timing based on the master ready signal and activation of master ready signal at slave ready signal without the help of the clock. There is no clock, please remember, there is no clock signal to derive the timing. Instead, you just use these two control signals to derive the timing, right? Okay, that's it guys for this session. Please go through all these topics carefully. Let us continue our discussion in the next session. If you have any doubt, feel free to ask. Thanks for watching. See you in my next video.